Okay. Hi. So welcome. And so this is a solution video for the big lecture for Air 10 from the 14th of October. So here's the problem. So we want to find the number of order sequence of 36 digits that have the property that the sum of the digits, and then that when you take the sum of the digits, and then you take the last digit of the sum, the digit is not in the original sequence. Okay. So 36 seems rather random, so we can just initially set 36 to n. So now we can just do n. Now we can solve everything in terms of n. So yeah. So some notation we're gonna be using is sigma of n. Actually, s. Sorry, to be the last digit of the sum of the digits of s. Okay, that's okay. So now we can let d. So we're just going to be using a bunch of notation here. So we can be let D be the set of all possible sequences for n digits. Okay? And so we can just simply let Si be the set of the digit sequences such that Si is equal to omega S, the ith digits of S. And so what we want to find is basically the size of the set of all possible sequences minus, and this is minus in set notation, the union. So this is the union notation. So basically, what this here means, what this here means is just S1 union S2 union S3, so on. Okay. So yeah, so in S3, so on to Sn. And the unit is basically just the union of these two circles is the shaded area. So that's kind of what union is. And of course, extended for more values as well. So this is basically what we're trying to find. So now this is a PIE problem. So now we can see how this is going to be PIE. And so if you don't remember, PIE is principle of inclusion and exclusion. And what it is basically the size of, so the basic definition is the size of the intersection of, well, any sets, but like, is the sum of the sizes of each of the sets minus the sum of the pairwise unions of the sets. And if there are more, like, and this can repeat onward until um, any number of sets, because after a pairwise set is 3, is basically you're taking the 3 sets and you're adding them and so on. So I'll just finish writing this out. And then, okay. Actually, sorry. This is writing the wrong way the whole time. Sorry. Sorry. Anyways. Sorry. So the union of it's the union of the set of n sets is equal to the sum of the sides of the sets minus the sum of the pairwise intersection of the sets plus the 3y's or whatever you want to call it. Basically just any any triple of sets and then minus the 4 tuples and so on. Expressed out, that would just be something like A1U. Sorry, S1 all the way to Sn is equal to the sum from I equals 1 to n of Si minus sum from I equals 1 to n, sum from j equals 1 to I minus 1 of Si intersection Sj plus and so on. So now we can use the principle of PIE to solve this problem. So what you get is that this value here is equal to sum from the sum over all sets J that are any subset okay that are basically J is any set from the set of numbers from 1 to n, including the set of all the first n numbers also. First n positive numbers as well. And so this sum is over -1 to the power of the size of j, which is basically what determines this negative here. If this is a minus or a plus, this determines whether it's a minus or a plus, and this determines the size, which is I think pretty self-explanatory as just this part. Yeah. Actually, to understand this better, I can probably express it better like this. So this value here corresponds to this part, or this part, and so on. So yeah. And so a digit sequence is not just mean that a digit sequence is in SI. SI if and only if the n minus digits that are not equal to not 1, add to a multiple of 10. So that's basically the only way that this holds true. So that means that the size of each SI is equal to the size of each SI is equal to 10 times 10 to the power of n minus 2, which is 10 to the power of n minus 1. And that's because there are 10 ways to choose the ith digit, and the rest of the digits, there's 10 to the power of n minus 2 ways. And when you multiply them out, you just get this. And so for any subset, really, J, that's a subset of the set of numbers from 1 to n. you can do something very similar. So if a string s, so where s here is a string, is in the intersection of the sj's, then you can have the sj is equal to omega s for all j in zj. So if you forgot what omega here, we define it to be the last digits of the sum of s. Okay, also these are all j's. And so there are 10 ways to determine this. And that determines the sj. And so from there, that just means that there are just 10 to the power of n minus j minus 1 ways to pick the remaining digits if all but one are fixed. And the last digit is uniquely determined. And so that just means that the number of ways here is just 10 to the power of n minus j. Because there's a minus 1 here, and we're multiplying by 10, so they just go away. And so there's one special case, and that is if j is equal to n. So if the size of j is equal to n, and that means, and the reason is because not all values of sigma s lead to solutions. So if j is equal to, the size of j is equal to n, then j is the set from 1 to n, set of integers from 1 to n, and so the last digits of n sigma s is equal to sigma s. And so the number of ways this happens is just GCD of n minus 1, 10, because if, so yeah. So the way this works is just kind of because you can take n plus 1 and then you do some stuff involving 10 with it because mu of s is just a digit and that's all you get. And so now you can compare the, so, so this is kind of hard to calculate right now, and so the way we can do this is we can compare the results from PIE to the binomial expansion of 10 minus 1 to the power of n. And so the binomial theorem states that 9 to the n is this, which is the sum, which you can turn into the sum of the sum over all subsets of the first n positive integers times -1 to the power of the subset times 10 to the power of n minus the subset. And as you can see, this compares. So now we can see that this compares quite well with the value of PIE from up here. If you, of course, did this part as well, adding in these two facts as well. And so that just means The only thing that it doesn't agree is when does not agree when j is equal to the set of the first n positive integers. And in this case, you're subtracting the net result. What you do is add in -1 to the power of n times GCD of n and 10. Oops, sorry, n minus 1 and 10, and you subtract -1 to the n, because this is from the binomial theorem, and this is the actual value from our PIE. So the final value for this, which we know is actually our final answer, is simply just 9 to the power of n plus -1 to the power of n times the GCD of n minus 1, 10 minus 1. And so for the case of 36, the GCD is 5. So this is 4. And n is even, so this is just 1. So this is equal to 9 to the power of 36 plus 4. And that is our answer. So thank you for listening. And yeah, thank you.